at coordinate psi, that's a material coordinate of that point. Now we consider another point Q, right, which is at psi plus d psi. Right, just coordinate psi plus d psi. Then I have a third point Q prime, which I would call is at psi plus d psi prime. Give a prime to it, and that I call Q prime. Now at time t, this is shifted, let's say, to coordinate x. This, I will say, has shifted to x plus dx, and this has, let's say, shifted to x plus dx prime. So now first part of the problem is to show what is to find out what is d by dt of dx dotted with dx prime. Right? If you look at how we did this, somewhat similar to how we did this for d by dt of dx dotted with dx. And if you recall that, ds square, this is ds square, which is slightly different, because that is the dot product of dx with itself. That's the length of the element. Now what is dx dot dx prime? It is now, you're considering two vectors. So we know that a dot b is cosine of the angle between the two vectors a and b, right? So if the two vectors are the same, obviously I would get the magnitude of a square, because cos theta is 1. Here I am going to get the angle, right, into the picture. On top of it, I also have the length of the two vectors, which may be different from each other. Right? So that's what it is. If you recall this side, wrote it as d by dt. First I showed that d by dt of dx is equal to, what was it equal to? It was equal to dx dotted with the gradient of d. That's what I first showed, right? Then this, which is d by dt of the length, this is a scalar. So I said that this can be written as d by dt dx dotted with dx plus dx. And if both of them are same, this is a scalar product, d by dt of dx dotted with dx, and this is dx dotted with d by dt of dx. So I can write this 2 times, right? D by dt, you can write it any way you want, but I wrote it this way, dotted with dx, from which I concluded that this is 2 times dx dotted with dx. That was the proof. So the proof for this will proceed along very similar lines, right? D by dt now of dx dotted with dx prime, right, is d by dt of dx dotted with dx prime plus dx dotted with d by dt of, because here you cannot write this 2 times because the two vectors are different, right? So now I can take use of what I already have, right? So this would be dx dotted with prime plus I have to show that this is actually, if I want to prove, right, d by dt of dx prime I have to show that it is actually problem with this. What I have here let me write out what I have here, what I have given to you. I can sort of get this now, which term now corresponds to which. Okay, this term has to correspond to this, it looks like. Right? Now this term, sorry, yes, this is clearly this. Right? Now I have to prove that the other term is actually given by this. Right? So too many dot products, but anyway, it can be shown. What I have to show clearly is d by dt of dx prime will actually turn out to be dx prime dotted with, and yet you're trying to prove that, because you have to be very careful, because differentials are always a problem to interpret. Right? The best thing is to look at what dx prime is. Right? Dx prime, what is it? Right? Dx prime, this is x. Dx prime is this vector. It's x plus dx prime minus x. Clearly that is the vector. Right? The best way to look at this, in my opinion, is to know that dx prime, the vector, is, of course, x plus dx prime minus x. But now I'm going to write this differently, then you see the clear meaning of this, because I'm always relating it, because I have to take finally the material derivative. So I have to express it in terms of the material coordinates associated with those points. That's why I'm introducing those material coordinates. You have to understand why I'm considering where they came from, because after all, the actual expression is going to look at the time rate of change of what is happening to these 3 points at the instant t, which is why I have listed this. That time rate of change is the material derivative, so I am following the same 3 points in motion. So I have to express them in terms of the material coordinates, then the meaning also becomes very clear. Clearly this is, right, this is coming from here, phi plus d psi prime. So that is now the function x, which relates x to the material coordinates, of c psi plus d psi t. That's what it is. That is what the meaning of the transformation is. It gives the coordinates at time t of a point that occupied a certain position in the reference configuration. Right? So I have the time t here. Now what is the, this is actually d psi prime, minus that is the vector x, because that is where it is coming from. Right? So now this can be expanded. Sort of consider this like a Taylor series expansion and chopping off the second or higher order terms. But by writing this in terms of the differential, I'm effectively doing that. Right? So this one clearly be dxi by d psi j times d psi j prime, right? The ith component of this. So what I will get is dxi prime, ith component, because I will get, or if you want the vector dx prime, this would be di. I just want the ith component, so that would be the vector. So I'm just expanding this around the point psi t. T is not changing anyway. So this is what I will get. The differential is d psi prime, which is actually d psi 1 prime, d psi 2 prime, d psi 3. So this is what I will get. So when I'm looking just at the ith component, this is what I will get. Now, I'm sorry, this is prime. That's the difference between dxi and dxi prime. Right? So this will have d psi j prime, whereas that would have simply d psi j. Then you follow the same procedure that I adopted in the earlier case. You now get a d by dt of dxi prime to be d by dt of d psi j prime. This again I can interchange the order of a differentiation and write this as sum over j, that is implied. Right? So dx1 by dt is nothing but the first component of the velocity, or I am looking at I, is dI by d psi j, d psi j prime. Then, now I want the gradient of the velocity vector field. So again, now I will express this. Looks at vi expressed as the signs. Now I want to get the x in. So I can write this as dvi by dxl times dxl by d psi j prime, and I would simply get this as simply dxl prime, and I can write this as dvi by dxl times dxl prime, right? Which in turn can be written as dxl prime dvi by dxl. So this is the dxl prime. This is the Lith component. This is L. This is the Lith component of the velocity gradient tensor. So from this I can conclude that d by dt of dx prime is equal to dx dot prime dotted with. So the final result looks quite obvious, because for dx I am getting this, so you might even guess that this is what I should get. That sequence of steps I have followed makes it very explicit. Right? There is no room for confusion. So this is what I have. So now I have dx dotted with this. I can also write this as, this is dx dotted with dx prime, right? So I can clearly interchange the order of the dot product. So I will effectively get this. This dotted with dx is the same as dx dotted with this. Right? So that you can easily verify. So finally I get the result that I want. The next step is to prove that this is actually equal to 2 times, but the two are not equal now, because earlier we had 2 times dx dotted with the velocity gradient tensor dotted with dx. Then we showed that the antisymmetric part of the tensor, the velocity gradient tensor, does not contribute anything to the sum. So I wrote this as dx dot this one. Right? So I wrote this as, so this would turn out to be dx 2 times only difference. Here, because the dx and dx prime are different, I get two terms looking like this. Right? Now this, we will substitute for this is d plus omega, and I showed that contribution coming from omega is actually 0. So I concluded that that is equal to 0. I mean, that's not equal to 0, that's equal because the other part is 0. So I get this. Here, though, the two terms are different, but it can still show that the net result will involve only t. So one way of showing it is to what I want you to prove is do the same thing we did earlier. Put d plus omega and look at the omega. That is one way of looking at it. Just look at what I am suggesting is this. You now look at this. Calculate that, and I get you to show that the two will add up to 0. Each term by itself will not be 0. The two terms together would add up to 0, so we will only get the term involving d, right? And we can easily show that when you have d in place, the two terms will be equal to each other and they can be written like this. That proof I will let you do it on your own. But we will now see the net result of what we get, assuming that that is the case, right? What do we get? What I have now is that the last part of it, I'll let you prove it. Right? It's quite easy to prove. This is not the only way you have to do it. You can just expand it out and easily prove that it would have to reduce to this. Because the answer is given, you can easily combine the two parts. Right? One easy way to do it is like this. Write out both of them. Because d is nothing but half times the gradient of V plus gradient of V transpose. So if you change the indices on one of the terms, you will get in one you will get dV I by dxj, and another you will get dV j by dxj. You can easily combine the terms and prove it directly. That's one way of, there are many ways of proving these identities. Another way, you can prove it in all different ways. This will just be an exercise and you understand this operations involving the change of indices and so on properly. What I would suggest as a second alternative would be to calculate the contribution coming from omega and prove that it is 0, and that the contribution coming from d would be such as to make the two terms equal to each other. So prove that separately and get the final result. So this is what I have, and so now this is. Now when you expand this, this can be written as d by dt of ds times ds prime times the cosine of the angle between the two vectors. ds is the length of the vector dx, ds prime is the length of the vector dx prime. Now I have this can now be written as dxj dji dxi prime. So now expanding that also off. So now this can be further simplified. I can write this as ds ds prime times d by dt of cos theta right plus cos theta times d by dt of ds prime. I can further simplify, but I am not going to do it because for my purpose I don't have to simplify it further. So this is what it is. Now what I do is divide throughout by ds times ds prime, or I don't even have to do it. Let's leave it like this. Now what I will consider, what you have been asked to do. Suppose now I have P, right? We just move to this point and Q is here, let's say, and Q prime, let us say, is here. So I now consider three elements, right, which are perpendicular to each other, so that the PQ element, right, is oriented along the O1 direction. So PQ is, that is dx is dx1 E1, and PQ prime, which is dx prime, is dx2 prime E2. So I can consider like that. Right? So I am considering 3 points such that PQ is perpendicular to PQ prime. So I am making dx to be oriented along O1. Now I have another element that I am making it oriented along O2, right? Then you can see what happens to this equation. So what is the angle theta between the two elements? 90 degrees, right? So d by dt of cos theta can be written as sin theta, d by dt of theta minus sin theta. Right? Minus sin theta d theta by dt. So sin theta is here 1. At that instant, I am considering instantaneous rate of change. So everything is instantaneous. Right? So sin theta is 1. Cos theta is of course 0. So I don't have to consider this term entirely. It is just vanishing for the particular case I am considering, not in general. Right? So then I get minus. So what will happen to the right hand side? How many terms will come again? Only one. Who said 1? Who said 1? Somebody said 1. Okay, I am saying 1. Can somebody write down that one term? Somebody else write down that one term. Sachin, can you write down what that one term would be? It's not difficult to do. It will help you do it. Yeah, so expand this for this particular case. So what I am saying is dx is equal to dx1 E1, dx prime is equal to dx2 E2. So just guess. I have said it is only one term. So guess that one term. dx2 prime. Guess that one term. What would be the value of j for that one term? Huh? J would be 1. Yes, fine. So write it. So j is 1. What about I? There are not many numbers there. There is 1 I can see, and then yeah, 2. Write it then. Now complete. Write that term 2 times. So what would you write for dxj? You say j equal to 1. Yes, E1 is not there. It is just a scalar, the length. There is no vector. I have written out the fully expanded form. dx1, yes, d 1, 2, and then 2 prime. Yes, that's correct. So you understood the meaning of what you wrote, so what you answered is correct. Go back. So dx1. This is the only term that could come. You can easily verify that that is the case because j, the index j, runs from 1 to 3. So you can look at it that way. So j runs from 1 to 3. So those are the components of dx, but it has only one component. So j, among all the terms you consider for j, right? Only the value of j equal to 1 will contribute because dx2 and dx3, which are the components of the vector dx, are 0 in this special case. Right? So the same, because if you are confused as to how only one term is coming, so I can write this as 2 times dx1. dx2 is 0, dx3 is 0, so only one j equal to 1 alone will contribute. Now I look at this, dxi prime, so that corresponds to the prime vector. Right? It has also only one component. That component is along the direction e2. So that will be, so the additional terms, they are all 0. dx3 prime is 0, dx1 prime is also 0. Because dx prime is, you can write it as dx1 prime e1 plus dx2 prime e2 plus dx3 prime e3 in the general case. In this special case, I consider it to be oriented along e2, the upward, vertical on the board. Right? So clearly the other components are 0, so plus 0 plus 0. 0 is not corresponding to the elements of d. Right? You will have d11 and d13 also coming in, but those contributions for the dx1 prime is here 0 and dx3 prime is 0. So this is all I will get. Now clearly ds is nothing but dx1. Right? So I get dx1 prime d theta by dt minus is equal to 2 times d12 dx1 dx2 prime, right, from which I can write d theta by dt, or rather d12 to be minus 1 by 2 theta by dt. In fact, I can call as Aris does, I can call this theta 1, 2. This now gives a meaning to the off-diagonal elements. The negative of half, you disregard that for the moment, d theta by dt here corresponds to the rate of change of angle of two fluid elements or vectors which are oriented along the O1 and O2 direction. If you consider such a fluid element, then the time rate of change of the angle associated with that particular set of elements, the rate of change of angle is directly related to the off-diagonal element d12. So you can easily guess, because d12 is equal to d21 because d is a symmetric tensor. Right? Similarly, d13, to consider d13, I only have to consider two elements. One of it is oriented along the O1 direction, other is along the O3 direction. If you consider that at the instant of time t, then the time rate of change of angle of between those two vectors would be directly related to d13 and similarly for d23. So this is often what is called as the off-diagonal elements correspond to what is referred to as a shear, right? It has to do with the rate of change of angle of two vectors which are oriented along the coordinate directions. That will directly give the off-diagonal elements of D. So we've given a physical interpretation of both the diagonal elements, which is simply a rate of elongation of an element oriented along any of the coordinate directions. That is what the diagonal elements would give. Off-diagonal elements correspond to the rate of change of angle of two vectors which are oriented along the any two perpendicular directions you may choose from O1, O2 and O2. Yes?
If theta was not 90 degrees, this would not be there.
This would not be the expression. That's why I am considering it that way. Because if we want directly the effect of the off-diagonal elements, pure, each one of them separately, then I have to consider like this. Just as I could have considered the rate of change of length of any vector oriented in an arbitrary direction, then I get the contribution of all the elements. So if you want to isolate, right, the effect of each one of the elements of D, then I have to consider like this. So for the diagonal elements, I first consider a vector along the O1 direction and see what the rate of change of length of that is. That will be directly given by D11. We want to find the D22, D33 similar. We want to find the effect of D12 alone. Then I have to consider two vectors, one oriented along O1 and one oriented along O2 through the angle. That time T is 90 degrees. The rate of change of the angle will be directly given by D12. Whatever, minus. Minus, yeah, minus is there. Oh, dx2 plus. Yeah, so those will get cancelled. Yeah, that is true. dx1, dx2. Because the prime element is oriented along the O2 diagonal. Yes.
Sir, if theta is 180 degrees, can we consider this as shear stress directly?
No, theta is 180, what would happen? Minus you will get. This is 0.
Same thing plus sign.
So you don't get the theta by dt. We have to see what it gives.
Then it directly becomes shear stress.
Shear. We have to see what that means. Are there any further questions? But of that we have to understand what is meant by shear in the most general sense. We clarify that in the next class. I can't see anything directly coming out if theta is taken to be 180. Right? This is the rate of change of angle is what the off-diagonal elements give. They are often referred to as causing the shear. They are often referred to as shear stress. You see the meaning of that later. Right? Any other questions? Now we come to the last part of the third part. We have already seen how the rigid body rotation can be represented as in terms of a vector as well as a tensor. What you are here required to show is that the angular velocity vector associated with the antisymmetric part of the velocity gradient tensor is equal to the curl of what I have here is omega k is half that's a k component I am considering. So what would you substitute for omega ij now? Half of that, right? So this would be half. If this is to correspond to the antisymmetric part of the velocity gradient tensor, that would be half times. Here we have to be careful because the symmetric part is just adding. So it doesn't matter which two you are adding first. But here it's negative. So it's delta, the gradient V minus the gradient V transpose. So the gradient V is actually Vj comma I. So this would be Vi comma j. So I can write it as two parts. So clearly you can see that it would have to correspond to the kth component of something, and if your answer is also given, it has to be to the curl of the vector v, right? So what can you say about the kth component of the curl of vector v? someone read out from the formula table? What can you say about the kth component of the running out of time? No, right? Take away the epsilon k ij comma I. Right? So now how would you bring this into that form? That is the question. Kij. If I want to get to Kij, two transformations. So I can write this as epsilon Kij Ej comma I. So I got one part of the answer. Right? So now this is minus Kji. So I just have to interchange once. Right? And I get Kji. But I am interchanging only here.
Plus.
Minus or minus. But the formula is
No. Hold on. I want Ej comma I. Right? So first I would transform throughout. Okay? Ej Ej comma I. And now interchanging I and j throughout the sum. This represents the sum over I and j. Because I want that Ej comma I. I can work in any way I want. Right? Since you have given this is correct. Kij Ej comma I. That's correct. Right? So here, because I want Ej comma I, because what I have is Pi comma j. So I interchange I and j throughout that sum. Ej comma I. Now I look at Kij. If I interchange once, I get Kij. Now I interchange only here, right? So that would be plus Bj comma I. Right? So this is both are the same. Both are the kth component of the curve of the vector. So they will add it to 2 times. So with 1 over 4, I get this. So the proof is complete. Right? I will let you. We'll discuss the 4th problem in the next class on Thursday briefly. How to prove the invariance of the 3 quantities and the transformation of coordinates. You see how to do that. You can easily attempt to do it. What you have to remember is that the transformation is actually an orthogonal transformation. So L transpose equal to L inverse. If you remember that, then it's very easy to prove that. Right? So we'll